In this video, I'm going to be talking about a type of volume question that's really common on the AP exam, where they're going to give you a region in the plane that's a base of a solid, and the solid is going to have known cross-sections, like cross-sections perpendicular to the x-axis or squares, or maybe cross-sections perpendicular to the y-axis or semicircles, something like that. And there's always going to be the word cross-section in the statement of the question. So the first one I've got for you is a pretty typical one, except for maybe we're probably not too likely to see one where cross-sections are rectangles with height 5. Really, that's just going to make it too easy. That would turn our figure into a prism, and we would just find the area of the base and multiply by 5 is what's going to end up happening. But I like this one because this is a good way to get us started. So R is the base of a solid, R being the region bounded by the x-axis in the graph of y equals 7x minus x squared. Cross-sections of the solid perpendicular to the x-axis are rectangles with height 5. Find the volume of the solid. Okay, so we're doing this, at least for the first one, it's all going to go back to the idea of the Riemann sum. And so this is the base of the rectangle. Oh, slipped a little bit. The height is going to be 5. I'm going to try to draw that. Okay, so that'll be 5. And you can envision it like, kind of stacking up a bunch of Polaroids or something. And then for this one, I'm going to give it a little bit of thickness, and we're going to call that thickness. Let's see if I can draw it right. Yeah, there we go. The thickness is going to be delta x. And we know we can find the volume of this, what looks like a rectangular prism, by multiplying length times width times height. So the volume is going to end up becoming, the sum of all of these rectangular prisms. Okay, so that's 5 times base times delta x. And then just like when we were doing the volumes with disks and washers, okay, we were looking for radii. Right now we're going to be looking to express the base in terms of x, right, because we're moving along the x-axis. Okay, and as the number of, little pieces of volume goes towards infinity and delta x goes towards 0, we know that this is going to become an integral of, 5 times the base dx. Now, 5 times the base is the area of that cross-section. So in general, what you're going to see me write is we're going to write that volume is going to equal the integral of area dx or dy. In this case, we're letting x run from 0 to 7, so let's put that there. Okay. So I've cleared all this out because all I'm going to need is that little representative rectangle, that cross-section perpendicular to the x-axis. And what I'm going to first do is I'm going to write down the area of a rectangle is base times height. Okay, height is always 5, so that's going to be b times 5, so that's 5b. Now I need to write down an equation for b in terms of x. Okay, so this base is really just the height of the graph at a given x value, so it's going to be 7x minus x squared minus 0, okay, because it's from the curve to the x-axis, which is the line y. Okay, so now I've got b, and I know that volume, like I said earlier, is the integral of area. Okay, cross-sections are perpendicular to the x-axis. That means we'll be sliding along the x-axis. We'll be integrating with respect to x. Okay, and I've got a formula for area is going to be 5 times the base. And I have a formula for the base. Okay, so that's going to be 5 times 7x minus x squared. Okay. Now in this video, in the interest of time, I'm only going to be setting up, but not evaluating these integrals. But if this is something you need practice with, go ahead and either factor out the 5 in front of the integral, maybe distribute it to the 7x and the negative x squared, integrate it, see if it's a good place to practice. Next, I'm going to work with the same region, except I'm going to build on top of it cross-sections perpendicular to the x-axis are squares. Okay, so this is, kind of similar to the last one, except for, okay, here, the height of the object is going to be considerably more than here, okay? because remember the height of a square is the same as its base. So this is going to be kind of a strange looking object, but we're going to take the same approach to write an integral to represent the volume. So I'm going to start with the area of a square. Well, you take the base of the square and you square it. That's why it's called square. So I need to write down an equation for b in terms of x. In this case, it looks like, again, b is going to be 7x minus x squared minus 0, top minus bottom. And we know that volume is going to be equal to the integral of the area. Okay, since cross sections are perpendicular to the x-axis, it's going to be with respect to x. And it's going to be as x runs from 0 up to 7. Okay. We've got area as base squared. So what I'm going to do is I'm going to take the base, which is 7x minus x squared, and I'm going to square it. And then you can carry out that integration on your own. If you were to try to do this by hand and not use technology, you would need to square the integrand first. You would need to, actually expand that binomial, but then it wouldn't be too hard. That's definitely something you could do. Next, we've got semicircles. So, same region, cross sections perpendicular to the x-axis are semicircles. Okay, so that's going to make some kind of, it's going to kind of look like a croissant. It's going to be kind of higher in the middle, getting smaller on the edges, and all of these cross sections will look like semicircles. Let's see if I can draw y'all one of these. Okay, if you can envision that standing up above the region, and a bunch of those, that would be, what the solid would start to look like. Okay. Now the thing about this is, I'm going to actually kind of draw this again. Yeah, sure, that works. And the area of a semicircle is half of the area of a circle, so it's half of pi r squared. So what we're going to need is a radius in terms of x. Okay, so this is going to be the radius, just this upper half. So what it's going to end up being is r is going to equal half of the height of the function. So it's going to be half of top minus bottom, which is 7x minus x squared minus 0. Okay. And I find for these, especially when you're going to end up putting them into the calculator, it's easiest to write this as 7x minus x squared divided by 2. Okay. And I know that when I see, cross sections perpendicular to the whatever axis, it's going to be volume equals the integral of area. Okay, still going perpendicular to the x-axis. I will give you a couple of examples perpendicular to the y-axis. And x is running from 0 to 7. Okay, so this is the integral from 0 to 7 of 1/2 pi r squared dx. So I'm going to factor out the 1/2 and the pi and make that a pi over 2 times the integral from 0 to 7. R is this fraction, this 7x minus x squared divided by 2. So 1/2 pi r squared dx. And then this is something that you could, if you really had to, you could expand this by hand and you could find the integral. It would probably be pretty unpleasant. Or you could use technology and give you a pretty decent answer to. The last one I've got with this particular region is cross sections perpendicular to the x-axis are isosceles right triangles. And now usually this will come with some sort of disclaimer so that you don't get confused. But they always mean the same thing. Isosceles right triangles where one of the legs is sitting as the part of the base that's perpendicular to the x-axis. Okay, so let me just draw a couple of pictures here. Okay, let's look at a isosceles right triangle. Okay, right triangle means it's going to have two legs that sit at a right angle. Isosceles means that those two legs are probably going to have to be the same length. Okay, because isosceles is two legs have the same length, and nothing's going to have the same length as a hypotenuse. So these two legs have to have the same length. And so we'll call this the base. And notice that this is just half of a square. So the area of an isosceles triangle is going to be half of the area of a square. Okay, so half of the square base, right? Because this is base. You could look at it as 1/2 base times height, also, if you like that. And then one of these legs is this, okay, if I draw it the same way. Okay, I'm not going to try to draw the triangle sticking up out of the region. I feel like that probably wouldn't go all that well. So I'm just going to say that's one of the legs. The triangle is sitting up above that, and we're going to integrate this area to get the volume. Okay, so we know that volume is going to equal the integral from 0 to 7 of area. Okay, this is going to be 1/2 times the square of the base. Okay, well, it looks like I forgot to write down the base. So I'm going to need to do that right now. Base is going to be just the height of the function again, top minus bottom, 7x minus x squared minus 0. And so I'm going to put that in for the area, right? 1/2 times the square of the base, 7x minus x squared dx. Okay, and that's going to be the volume. That's an integral that represents the volume. You can take that yourself. You can use a calculator. Oftentimes these questions, especially in free response, and sometimes even in multiple choice, are set up but don't evaluate. In multiple choice, how that would look is they would talk about this solid that has R as its base and cross-sections of it perpendicular to the x-axis are isosceles right triangles. And they would say, which of the following integrals represents the volume of the solid? And you'd choose from a few different integrals, you know, all but one of which had something wrong with them, and you would go from there. Okay. Next, I've got one where I just kind of decided that I would make a region trapped by the graph of y equals log x, the x-axis, and the vertical line x equals e to the 5. Okay. Now, important to note that the y value here is going to be 5 because, of course, I'm going to say cross-section is perpendicular to the y-axis. We haven't done any of those. That's what we needed. So, and that's just the case because the height of the graph of log x at x equals e to the 5 is, well, log is the exponent. It's what exponent do I put on e to get e to the 5? I put the 5 exponent on e to get e to the 5. So cross-sections perpendicular to the y-axis are semicircles. Okay, well, let's go over here and... Okay, that's a cross-section perpendicular to the y-axis. The radius is going to only be half of that. Okay, so the radius will be half of something. We're going to do right minus left. So that's going to be x equals e to the 5 minus x equals, okay, I don't have an x equals for this curve. I have y equals, so I need to solve for x and get it in terms of y. So if y equals natural log of x, I'll take e to both sides power, and I'll say e to the y is e to the log x, which is just x. So right minus left will be x equals e to the 5 minus x equals e to the y. And so I know that the area of a semicircle is 1/2 pi r squared. Volume is equal to the integral of area, dy this time. And y is ranging from 0 up to 5. So let's say 0 to 5 of 1/2 pi r squared dy. Factor out the pi over 2. Substitute on r. Okay, so r is e to the 5 minus e to the y divided by 2. Square it, integrate respect to y. That's something you can do on the calculator. The last one I've got for you on volumes with known cross sections is one from 2011 Form B, number 3, for your response. Okay. And there were, I think the first part of this question was find the area of the region. Okay, so probably what I would have done, I'm sure you could get it in terms of y and do one integral if you really felt like it, but you could integrate 0 to 4, square root x dx, and then from 4 to 6, 6 minus x dx, which I wouldn't even do. I'd just do that as a triangle, right? It's going to be about height 4, or no, a height 2 and a width 2, so the area would be 2. Okay, don't need to integrate for that. Part B says the region R is the base of a solid. For each y, where y is between 0 and 2, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose base lies in R and whose height is 2y. Write, but do not evaluate, an integral expression that gives the volume of a solid. Okay, we can do that. Okay, perpendicular to the y-axis means I'm going to need to integrate with respect to y. Rectangles is thinking, oh, this is great. But a lot of people could be thrown off by them giving you the height in terms of y. Like, what is the solid even going to look like? And you should not worry what this solid's going to look like. You should worry about how am I going to write an integral to represent the volume of the solid. So we know that the area of a rectangle is base times height. Each cross section perpendicular to the y-axis, so that's this, is a rectangle whose base lies in R and whose height is equal to 2y. Okay, well, I know that height equals 2y. That's one less thing to worry about. Base, I'm going to do right minus left. Okay, so it's going to be x equals, well, I don't have x equals. Okay, so what I would need to do is I could say y equals square root x and then solve back and I could get x equals square root y. I'll say f inverse of y equals y squared. And over here, g inverse of y is going to equal 6 minus y. So that's like saying x equals y squared and x equals 6 minus y. So base will be right minus left. Okay, the one on the right is the line, so that's x equals 6 minus y. And the left is going to be x equals y squared. Okay, so that's 6 minus y squared. I might like that, make it a little easier to look at. Okay, and now the volume is going to be the integral of area. And y is going to run from 0 to 2, it looks like. Okay, now I'm going to plug in on area. Area is base times height. Okay, so the base is 6 minus y squared. The height is 2y. And you see that, okay, they told us just to write an integral but not evaluate it, so that's where we're going to stop. But this is definitely the kind of integral that we could go ahead and take if we really had to. It wouldn't be too bad. And I think that's going to do it for the volumes with known cross sections. Actually, hold on. There is one more that I'd like to show you. Okay, so from 2010 Form B, the first one, okay, so this is a calculator question. Well, I was talking about just one of these regions. The first part of the question was find the area of R. That's not too hard. Integrate top minus bottom, so integrate 6 minus 4 log of 3 minus x from 0 to 2. Use the calculator for that. That's really friendly to us. We would love to see a question like that. Part B is find the volume of the solid generated when R is revolved around the horizontal line y equals 8. Again, that would be really nice. We should all be so lucky to get that on our free response. But the third part is really the one I want to talk about. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of the solid. All right, so let's get it. We know the area of a square is going to be the square of the base. We need a base. Okay, so here we go. Top minus bottom. So the base is going to be, the top is y equals 6. The bottom is y equals 4 log of 3 minus x. Okay, so this is equal to 6 minus 4 log 3 minus x. Okay. And so we know that volume is equal to the integral of area. Cross sections are perpendicular to the x-axis, so with respect to x, we're going to let x run from 0 to 2. And, okay, the area is base squared, so this is just going to become the integral from 0 to 2 of the base is 6 minus 4 log 3 minus x. Square the base, integrate with respect to x. Okay, you know, this was a calculator question in 2010. And I'm pretty confident that if y'all could get this far, you could type this in, use Math 9, and get yourself an answer with 3 decimal places. And so that is going to be all I've got for you today.